to Newton's law, the object will not accelerate because there is no net force acting on it. An object in equilibrium moves with constant velocity. Remember that staying at rest is a state of constant velocity. You've already analyzed several equilibrium situations in which two forces act on an object. It is important to realize that equilibrium can also occur if more than two forces act on an object. As long as the net force on the object is zero, the object is in equilibrium. What is the net force acting on the ring in Figure 14? The free body diagram in Figure 14 shows the three forces acting on the ring. The ring is not accelerating, so you know the net force must be zero. The free body diagram, however, does not immediately indicate that the net force is zero. To find the net force, you must add all the vectors together. Remember that vectors may be moved if you do not change their direction, angle, or length. Figure 15 on the next page shows the process of adding the force vectors to discover the net force. Figure 14. The ring does not accelerate, so the net force acting on it must be zero. Compare the vertical component of the force pulling up and to the right to the weight of the mass hanging from the ring.
Okay, so we have used spring scales before, have we not? Just on the last lap. So what's happening here is you have an object in the middle. You have somebody pulling here, somebody pulling here, and somebody pulling here. Now, it's not one spring scale, it's three. Are they pulling in different areas, different ways? Do we know if they're all equal? How do we know they're all equal? Because I'm telling you they are. How do you know? Is the ring moving? Stationary, right? So if you're drawing these, do you see these vector forces here that could be right here? You have your force A, you have your force B, you have your force C. It doesn't look like this one is equal, does it? Or is that not a spring scale? What is that down there? It's a weight. Okay? So we only have 2 dimension, not 3. Do you understand the difference between 1 dimension, 2 dimension, and 3 dimension? If it was 1 dimension, it would just be you pulling it one way. 2 dimension, 2 different forces are acting. And if this was another force, that would be in 3 dimension. These two, do they look like they're about the same vector? Do we have a vector? Do you see any vectors at all? Nothing. What would the vectors look like? If we were using this little thing right here, which is this ring, and this weight on the bottom, how would we show the forces? What does our vectors look like? Okay? So the first thing we're going to do is we're going to put our dot, right, guys? Then we're going to think about what forces that we have. What do we have going down? Force gravity on the weight by the earth. Then we're going to have a force going in this direction, and we're going to have a force going in that direction. Is that the way it's going to look? So you've got force A, right? That's that person, not force applied. Here is your force C. That's that person, not it. Right? But what type of forces are they using here? Well, I like force applied. Is there another force that it could be? Force tension. Why would it be force tension?
Because you're pulling on it, so it's stretching out.
Has a spring involved, correct?
Yeah.
Do you agree? I think it's force tension more than force applied. Okay? So the force tension would be on what by what? On this ring, right? Got it? And it looked like this. If they were equal, what would we have to do to these vectors? Well, they've got to be the same length, right? And then those cancel out. Everybody good? Do we have another force here? No. There's no normal force. Why is there no normal force? Because it's hanging. It's not sitting on the desk. Everybody good so far? Was there anything that you wrote or drew on this page? No. Okay, let's go to the next page.
Equilibrants. Figure 15 shows the addition of the three forces, Fa, Fb, and Fc, acting on the ring. Note that the three vectors form a closed triangle. The sum Fa plus Fb plus Fc is 0. Now suppose you have a situation where two forces are exerted on an object and the sum is not 0, as shown in the free body diagram in figure 16. How could you find a third force that, when added to the other two, would add up to 0 and put the object in equilibrium? To find this force, first add the forces already being exerted on the object. This single force that produces the same effect as the two or more individual forces together is called the resultant force. In order to put the object in equilibrium, you must add another force called the equilibrant that has the same magnitude as the resultant force, but is in the opposite direction. Notice that in figure 15, the force Fc is the equilibrant of Fa and Fb. Figure 16 illustrates the procedure for finding the equilibrant for two vectors. Note that this general procedure for finding the equilibrant works for any number of vectors. Get it? Identify the relationship between the equilibrant and the resultant vector.
Okay.
Figure 15. The forces acting on the ring sum to a 0 net force. Figure 16. The equilibrant is the force required to put an object in equilibrium.
Okay. So when we drew our force before, right guys? We drew our force this way, in gravity, and we said these two cancel out. Isn't that what we said? Now what does it tell us now? How is it different? If I took a ruler and I measured A and I measured B, should C equal either one of them or both of them together? Okay, so based on that, instead of doing that like we've always done, how would we do this one? That's it. Right? Those two balance that one. Do you see the difference with this and that? Everybody good so far? Okay. Now, do you have to draw that? Now, I do believe that we had the resultant already. Did we not do that on Monday?
Yeah.
And remember what the resultant was? What was that? So let's think about this. Are you ready? Think of words that we've used already. If I start here and I go from here to here to here, and I wanted to know the total, what is that called? Plus b squared equals, no, equals c squared, r squared. But what I was asking was, if I wanted to know, and I said, all right, if from A to this spot here was 10 meters, and from here to here was 10 meters, right? What am I asking you for? What? I said you just walk 10 meters that way and you turn 10 meters that way. What am I asking you if I say it's 20 meters? The total what? The total distance, right? Now, what is the difference between distance and this number here? This is distance. What is this one called? No. No. Starts with a D. DIS, displacement. When do we do distance and displacement? Week number 2. Okay, total distance and displacement. Remember how we did that before, is we were drawing our little, remember? We said, all right, if somebody walked 10 meters this way, they came back and they walked 5 meters this way, and they marked another 5 meters that way. What was the total distance? 20. What was the displacement? Well, you take these two and add them together, right? 10 plus 5 is 15. Minus 5 is 10. Are you remembering? Do you remember distance and displacement? Okay, do you remember distance and displacement now? Okay, cool. All right, let's go to the next page. Now, before I go to the next page, if you forgot about distance and displacement, write that down in your notes, because you'll need to make sure you understand that, because it's coming back to haunt you.
Inclined planes. You have applied Newton's laws to a variety of situations, but only to motions that were either horizontal or vertical. How would you apply Newton's law in a situation such as the one in figure 17, in which you want to find the net force on the girl? First, identify the forces acting on the system. In this case, the girl is the system. The gravitational force on the girl is downward, toward the center of Earth. The normal force acts perpendicular to the slide, and the kinetic friction force acts parallel to the slide. You can see the resulting free body diagram in the final panel on figure 17. You know from experience that the girl's acceleration will be along the slide. Choosing a coordinate system. You should next choose your coordinate system carefully. Because the girl's acceleration is parallel to the incline, one axis, the x-axis, should be in that direction. The y-axis is perpendicular to the x-axis and perpendicular to the incline's surface. With this coordinate system, you now have two forces, the normal force and friction force, in the directions of the coordinate axes. The weight, however, has components in both the x and y directions. This means that when you place an object on an inclined plane, the magnitude of the normal force between the object and the plane usually will not equal the object's weight. Get it? Explain why you would choose the x direction to be parallel to the slope of the inclined plane. You will need to apply Newton's laws once in the x direction and once in the y direction. Because the weight does not point in either of these directions, you will need to break this vector into its x and y components before you can sum the forces in these two directions. Example problem 5 and example problem 6 both show this procedure. Figure 17. The girl's weight causes her to accelerate down the slide. Describe how the component of the girl's weight parallel to the incline changes when the angle between the slide and the horizontal increases.
Okay. So let's see if we can make this, because it looks like we're going to have to get up and go do something in there, because y'all heads are down. Oh, I'm sorry, you're on your phones. So, if we have a system, we identify a system by a circle around it, correct? We have always done our vectors like that, right? Our x and our y vectors have always been that direction. Now we're going to include an inclined plane. Where do we have an inclined plane in the lab that we've been working with? The ramp, okay? So if we look here, first of all, identify the system. Here's where the problem is. Your x and y is not perpendicular, it's slanted. Do you see how it's slanted? Okay? So when you do that, look what we have to do here. So if we look, this here is my x. This here is my y. But when I'm drawing gravity, where am I drawing gravity at? In the middle, right? Look where velocity is coming here. If I was doing force normal, where would that be? Looks kind of weird, doesn't it? But now we're on an inclined plane.
It says force normal is along the y-axis in the
That way?
body diagram.
Because she's sliding down?
I guess so.
Well, that's what it says right there, isn't it? Force normal?
Yeah, but it has the blue line.
Yeah, you're good. You're good. Okay, so if we're looking, first of all, with the motion diagram, thank you, sir. What are we looking at with the red? What are we showing with the red arrow? The velocity and how she's sliding. And like y'all said there, she starts off slow, right, guys? Like you said, and then she speeds up. That's really good. Okay. Why does it tell us acceleration is going in that direction? Right, you accelerate. And why is my force net going in that direction? Okay, so let's get up and go to the lab room because God knows y'all are not ready for some math problems. I'm telling you that already. These cheese things.